In this video, I'm going to do a quick introduction to KLEE, install it in possibly the easiest way, and also run through the tutorials on the KLEE website. So KLEE is a symbolic execution engine, and I don't really want to go into the details with what that is, as I assume if you are already here and watching, searching for KLEE, then most likely you are familiar with it, but otherwise there's a lot of literature on it online, and well, you will see some of the aspects of symbolic execution by watching this video. Okay, so we go to the KLEE website, klee.github.io, and they have been so nice to actually have, if we go to the KLEE website here, we can go to getting started, and we go to our Docker images, and then we can see that they have various ways to install it by way of Docker. I'm gonna go down here to the building the Docker image locally, and I'm gonna just go ahead and fire those up. Okay, going to KLEE, and then just build the Docker image. Building this Docker image can take a while, so I think in the video I will just forward this. Okay, so it finished, and I think it took about like 2-3 minutes. So once we have built the Docker image locally, we can then start to access this Docker image, and the simplest thing to try is creating a temporary container and gain shell access. So let's try and do that. Okay, looks like we're inside the container, and we can fire out the who am I, and we can see that we are indeed KLEE. You can now try running KLEE inside the container, where you should see an output similar to, okay. And it all looks fine, so KLEE 2.2, and we also have LLVM 6.01, and okay, so we have KLEE 2.1 here, that means they have updated since then. And what Clang version? I guess we have Clang 6.01, and indeed we do. Okay, so now let's just really go straight to the tutorials, since it seems that we have a working KLEE. If we go to the tutorials, let's do a first tutorial. This tutorial walks you through the main steps needed to test a simple function with KLEE. Here is our simple function. Okay, very simple getSign function. Let's do a little work directory here, and tutorial 1, and test C. We create a small C program. We have added our function that we're going to attack, or that we're going to analyze, and then we will add a main function that has a call into the KLEE symbolic execution engine. Okay, so now we actually have a program that will work. We have a main function. It declares a local variable a, and then it calls KLEE make symbolic, which will, and it passes the parameters, the address of a, the size of a, which is 4 bytes, and then also a string, which is the name of the symbolic variable that we will create. And that's a call into KLEE, the KLEE core execution engine, so we don't really, it will not be in our library, as it will be in the library of KLEE. And then afterwards we call the getSign function here, and the idea is that at this point when we call getSign, a will have a symbolic value. So when we call into getSign, x will have a symbolic value, and then KLEE will start to analyze what does it take for us to explore the different possible execution paths inside of this getSign function. So we can see that there is an execution path that checks if x equals 0, then we return 0, and if x is less than 0, then we return -1, and if x is not equal to 0 and not less than 0, that means it is above 0, then we will return 1. So there is 3 different execution paths inside of this getSign function. Okay, so for us to run KLEE on it, the first step is to compile the program to LLVM bitcode. And KLEE operates on LLVM bitcode. To run a program with KLEE, you first compile it to LLVM bitcode using clang emit LLVM. Okay, so let's do that. Emit LLVM CG, we want debug symbols, and then getSign. Oh, we have our file is called test.c, not getSign, so we change it a little bit. And also we don't really need these, so I'm not gonna include them, although we could include 0 optimizations. Okay, we get a warning, and we get a warning because, well, KLEE make symbolic is not defined in our program. We can ignore that for now because the function will exist inside of the KLEE symbolic execution engine when we start to analyze the program. So we could make it a bit more cleaner and include a header file where the KLEE make symbolic is defined, but for now let's not do it. Okay, so that gave us a test file, test.bc, which is an assembled version of the LLVM IR. And we can actually look at this LLVM IR by disassembling the bitcode. As follows, we use the LLVM dis for disassembler tool. And now we can actually look at the bitcode of the LLVM intermediate representation. And we can see that we have a function here called getSign, which is the getSign function from our program. We have a function here called main, which is the main function. And here we have the various LLVM instructions of the given program. And we can see here that there is a call to KLEE make symbolic here. And we also have a call to getSign. So that's looks very much like the main function that we have defined in our program. And we can see, although the variables here look a bit odd, essentially they contain the 3 arguments that we provided to KLEE make symbolic. Okay, and also we can look at the different labels in the getSign function here. So we have a if then, if end, if then, if else, and these essentially correspond to the various different execution paths that there exist within the if statements of the getSign function that we have. And we can see that all of these different labels in the code store a value inside a LLVM variable called redval, and redval is also the value that is returned from the function that we can see down here. So the return instruction here returns the integer that is in the variable number 2, and the variable number 2 is loaded on from the redval, which is the variable that we stored the return value in. Okay, so let's not go too much into the details with the LLVM code. We will then try and run KLEE on it, and well, essentially we can just run KLEE test.bc, and sweet. Okay, so we got completed 3 paths, generated 3 tests, and it executed a total of 32 different LLVM instructions. And this corresponds very well to the output that we get from that's written in the documentation. Although we had 32 instructions and they have 31, that's probably just because of the different versions of LLVM potentially. Okay, so let's see what folders what was generated from KLEE. The only thing that was really generated was a KLEE out 0, which is a folder where all the kind of like artifacts from the run is stored. And then we have a symbolic link to that folder. And the reason we have a symbolic link is if we run the execution again, KLEE has just generated like a next index result folder, so KLEE out 1, and now we can see that the KLEE last symbolic link points to the KLEE out 1 folder. Okay, so let's see what is in one of these folders. We have the 3 different test cases that triggers that each of these test cases correspond to kind of like the input that executes a unique path in the program that we are analyzing. We also have an assembly.ll file which contains all of the LLVM code that was that KLEE used to analyze that KLEE used for its analysis. And this is important sometimes because KLEE will add some instrumentation to the code. Okay, then we go into KLEE generated test cases. Test case generated by KLEE are written with .ktest extension. These are binary files which we can read with the ktest tool utility. Ktest tool outputs different representations for the same object, blah blah blah. Okay, so instead we will try and fire up these commands. Ktest tool KLEE last ktest. Okay, so very cool. We can see here that the object, they have like the concrete data that was used for the given object that triggered this execution path, and in this case it's the variable a, which corresponds to this a here, so that's the name of the symbolic variable we created with KLEE make symbolic. And we can see that for this test case, which is one execution path, the value in interpreted as assigned integer was 0. And if we check the other test cases, we can see that here it is indeed the same symbolic variable that is in our test file, but the interpretation of the bytes that was the concrete representation of this given test case was assigned integer that is above 0. And in our first test case 3 I guess, we have a negative number in the concrete instance of the symbolic variable that we generated. So you can see here that indeed this corresponds to an execution path where the symbolic variable is equal to 0, where it's less than 0, and where it is above 0. And that's exactly what we have here: equals to 0, above 0, and less than 0. Okay, so let's go to the next tutorial perhaps, which is testing a simple regular expression library. And let's create a new folder for us. This is an example of using KLEE to test simple regular expression, to test a simple regular expression matching function. You can find the basic example in the source tree under examples regexp. Regexp contains a simple regular expression matching function and the bare bones testing harness needed to explore the code with KLEE. You can see a version of the source code here. Okay, so let's just copy this whole example. We can call it this time the correct one, regexp. And we have a main function, and we have a call to KLEE make symbolic, and we make the entire array of 7 bytes, 7 char, chars here. We make that entire array symbolic. Here's the address of RE, the size of RE, which is 7 bytes. And then we have the name of the symbolic variable that we will generate. And then we call the match function with our symbolic buffer, and also a concrete string called with the value hello. And the match function here, it does a bunch of pattern matching. It does a bunch of matching on the contents of the RE buffer here. If it is equal to that, a hat symbol, then we call match here, and if and we return the value of that. And otherwise we will just have do while loop that continuously calls match here, and the match here does even more checks on the buffer, on the RE buffer. And then we have also a final call here to match star, which also contains a do while loop and a conditional statement. So there's a bunch of different execution paths that this program can take. For example, this can be true. This can be true, and then we will simply call directly here. Or if this condition is false, we will go further down, and then we can have a given number of loop iterations that will, and each of those will consist of a different execution path. Okay, so let's try and run this through KLEE. And we will do the same thing as before. We have here the BC code of the Regex P. We can check out the BC code, the LLVM intermediate representation. And I will not go through it similar to the way we did before, but we can at least see that we have the match the function defined here. We have the match here the function. And we have also the main function. And do we have the match star somewhere? Okay, and we have the match star function here. Okay, so looks all good, and you can go through this yourself if you're interested in LLVM. Nonetheless, let's try and execute the code with KLEE. Let's just fire it on the BC code. Memory out of bound. So it found a bunch of errors. It found 2 memory corruption errors. And we can see that we get the same output as the documentation of KLEE said. And on startup, KLEE prints the directory used to store the output by default with KLEE. So this describes what I said before about the different KLEE out directories. So we can see that we got the KLEE out resulting directory here with the various artifacts from the KLEE run. And okay, so we have a lot of different test cases in this one compared to before, and each of these have the concrete value of the symbolic buffer here that executes a unique path in the program. So you can see that even this small program, we actually get more than 7,000 different execution paths. So even a small program like this can actually have a large execution space. We can also look for the error reports, which are postfixed with .error, and these show us where we had show us information about the memory out of bounds errors that KLEE found. So if we try and read these, we can get the stack trace, and we also get where in the assembly LLVM, the line in the assembly .ll file, which is inside the KLEE out directory, which instruction it occurred on, and we get the address that KLEE was trying to execute, and a bunch of a bunch of information about the error itself. We can look at the other one, which should be quite similar to this one. And indeed, it looks very similar, although the memory out of bounds was not at the same place. So let's just try and look at one of these lines, line number 23. Okay, so there is certainly a memory. There's certainly a memory, a read of memory here, and most likely this one checks if there is a null point, if the buffer is null terminated. So one could imagine that if the buffer here is not null terminated, then it will have an off by one read, at least an off by one. And that's probably what happened. I will not go into the details with analyzing that. One thing that we would like to see is we would like to see the value of the buffer that was that created the error states, and the way we can do that is use this k-test tool as we used before, and we will look at the test cases here, 19, and here we get the specific bytes that were used to trigger the bug of the given buffer, and we get the same, we get something similar here where we can see the raw bytes that actually triggered the memory out of bounds read. Okay, so that's it for this little presentation to KLEE. If you like it, please send me some email or something where you say you like it, and if you would like to see more, I would be very happy to hear from you, and I will in that case make more videos and potentially go more in depth with the topic of KLEE. I've used KLEE for quite a while and I really like it. It's an awesome tool. It has a lot of strengths, but it also has a lot of disadvantages. But I don't really want to go into the details here. I would like to, you can explore it yourself and test your curiosity. So thanks for now.